Hey everyone, and welcome back to the channel. Today, we're tackling LeetCode problem number 22, generate parentheses. This is a classic dynamic programming problem rated as medium difficulty, and it's a frequent guest in coding interviews. The problem statement is simple. Given an integer n representing the number of pairs of parentheses, we need to generate all possible valid combinations of parentheses. A valid combination means that every opening parenthesis has a corresponding closing parenthesis, and the closing parenthesis always comes after the opening one. For example, if n is 3, some valid combinations are 00000, 00010, 0010, 0020, 0120, and 1010. But something like Connie or Wasi is invalid. Got it? We'll explore different approaches to solve this challenge, so let's dive in. Understanding with examples. Let's solidify our understanding with a few examples. If n equals 1, the only valid combination is 00. Simple enough, right? Now, if n equals 2, we have two pairs of parentheses. Think about it for a second. We can have 00, where the inner parentheses are nested, or we can have 00, where they're separate. These are the only two valid combinations. For n equals 3, as mentioned before, we have 5 valid combinations. Seeing these examples helps us visualize the problem and understand the patterns involved in generating these combinations. We'll use this understanding to craft our solution. The key is to ensure that at any point, the number of closing parentheses never exceeds the number of opening parentheses. Brute force approach. One way to approach this problem is through brute force. We could generate all possible combinations of n opening and n closing parentheses and then filter out the invalid ones. This involves checking if, at any point in a combination, the number of closing parentheses exceeds the number of opening parentheses. While this approach will eventually get us the correct answer, it's highly inefficient. We'd be generating many invalid combinations before discarding them, leading to a significant time overhead. The time complexity of this brute force method would be exponential, making it impractical for larger values of n. We need a smarter approach, and that's where dynamic programming comes in. Our optimal solution uses backtracking to efficiently generate only the valid combinations. The core idea is this. We'll recursively build up our parenthesis strings, adding either an opening or a closing parenthesis at each step. Crucially, we'll maintain a counter to keep track of the balance between opening and closing parentheses. If the balance becomes negative, meaning more closing than opening, we know we've gone down an invalid path, and we can backtrack. If we've reached the maximum number of pairs, 2n, and our balance is 0, meaning we have a valid combination, we add it to our result. This recursive approach, guided by our balance check, drastically reduces the search space and delivers a much more efficient solution. Code implementation. Let's see the code in Python. We'll start with a function called generateParenthesis that takes n as input. Inside, we'll have a helper function, say backtrack, which takes the current string, the number of opening parentheses used, the number of closing parentheses used, and the max number of pairs, n. The base case is when we've added 2n parentheses. Otherwise, if we can add an opening parenthesis, we recursively call backtrack with an updated string and counts. Similarly, if we can add a closing parenthesis without making the count negative, we do the same. It's all about cleverly managing this balance using these recursive calls, ensuring we only generate valid parenthesis strings. The entire process becomes elegant and efficient with the power of backtracking. Time and space complexity. The time complexity of our optimal solution is O of the nth catalan number, which is approximately O of 4 to the power of n divided by n to the power of 3/2. Space complexity is also bound by the number of valid combinations, which again is the nth catalan number. While it might seem complex, it's far superior to the exponential time complexity of the brute force approach. This algorithm scales significantly better for larger values of n. We've significantly improved efficiency by avoiding the generation of invalid combinations. Engagement break. Before we wrap up, I'd love to hear your thoughts. Did you find this explanation helpful? What other approaches have you tried for this problem? Let me know in the comments below. And if you found this video valuable, don't forget to give it a thumbs up and subscribe to the channel for more coding tutorials like this. Hit that notification bell so you don't miss out on future uploads. Sharing this video with your fellow